Okay, so this is a video solution for the test 2 of the Form 3 Physics. Question 1. A load is suspended from a flat. The vertical force on the flat due to the load is 0.75 Newton. Calculate the mass of the load. For this one, we are given the weight and you are asked to find the mass. So therefore, essentially, we're using weight equals to mass times g, or W equals to mg to solve for the mass. So because of that, therefore, mass is W over g. W is 0.75, g is 10. So therefore, the mass will be 0.075 and then kg. Now the difficult part of this question is that some of you may not realize that the vertical force on the flat due to the load is the weight. So this is something that one mistake, and because of that, some of you will think that this is the mass. So many of you treat this as the mass and then multiply this by 10 so that to find the weight, but this is not true because first of all, it's very clear that they state this as in the unit of Newton already, so therefore it must be a force. On the other hand, when you read the question carefully, it already tells you that this is the force. So therefore, if you are careful enough that you are given a force and you want to find a mass, then actually this question will be much more straightforward. I remember many of you have finished the test earlier. If you have checked your paper very seriously, then you may be able to spot out this mistake and get back 2 marks on that. Many of you didn't have steps. That's so unfortunate, because if you make any careless mistake, then I have no hope to give you any marks for the calculations. Okay, now in figure 1.1 shows the load suspended from the flat. So this is the case. A wire is attached to the load at X and pulled horizontally to the right. So therefore, the real situation we have now is not just one wire. There's another wire which is pulled horizontally to the right. The tension on the horizontal wire is 1.2 Newton. So therefore, 1.2 Newton. Now, by drawing a scaled diagram or by calculation, determine the magnitude of the resultant of the force at X. So I'm finding resultant force, of which 2 forces are. One is due to the load. Second, due to the tension in the wire. Now, due to the tension in the wire is already here, the 1.2 Newton. Then how about the force at X due to the load? Well, the load is experiencing the gravitational force. So therefore, there is another force going down. We have calculated already. They give you already 0.75 Newton. So this will be the second force. So therefore, right now, we need to find the resultant force of these 2 vectors. Now, wrong way to do it will be 0.75 and then 1.2 Newton, and then you just connect the two heads. But this is wrong, because remember, we are using head to tail. Or if you remember, we are using a metaphor that we say we give instructions to a robot. We ask the robot to move to the right, and then ask the robot move downward. So here, then you will see, you will find head to tail. Now some students, when they come to talk to me, they have no idea about the fact that actually we can freely move this 0.75 anywhere you want. They kind of think, well, I know this is 0.75, it's there, but they do not know that actually they are free to move this force to anywhere they want. Well, at the bottom you see we have to move this 0.75 Newton to here such that we can have head to tail, such that we can have the correct metaphor, so that we have head to tail, so that that is the correct way of doing it. Now, so if this is one misconception that you have, that you think, the force is already here, how can I move it? Well, ask yourself, what is a vector? Vector has both magnitude and direction. And now, this vector is pointing down with a magnitude of 0.75 Newton. 0.75, direction is downward. I want to ask yourself, when I have a vector, here, if I move this vector to somewhere else, did I change the magnitude? Did I change the direction? Now, although the position of the vector, yes, is different. Initially it's here, initially it's here, now it's here, initially it's here, now it's here. But when I move this around on the paper, I did not change its direction and its magnitude. So therefore, even you move this vector from one place to another, you did not change it. It is still the same vector. Yeah, I put this here for you to reference. So these two are the same. So therefore, it's nothing like, it's illegal to move this force. The force is here. How can I move this force to here so that to make head to tail? Well, it is illegal. Because you didn't change the vector. It is still the same vector. Now having that in mind, therefore, when you draw the free body when you draw the force diagram, when you understand the question, well, it must be the case that you will have the two tails located on the object. However, when we are finding the resultant of two forces, we have to move them such that one head of a vector is now on the tail of another vector. So you have to move it. And what I discussed in here is that is it legal? It's okay to move the vectors around, because even you move them around, as long as you didn't change its magnitude and direction, they are still the same vector. Okay, so having all this, then we know that what kind of diagram we need to draw. Now, of course, we need to respect the scale, and to do that, I need to use a ruler. Let me do this. Here, like this. So I have a ruler now, and then now I'm going to draw two vectors that they have 1.2 Newton and 0.75 Newton. That may be on my ruler. Then I draw. Let's start from here. Can I draw here? Oh, okay, good. Now I have this one. I draw a line here. This presume means 12 cm. Now, which refer to 1.2 Newton. This represent the force 1. Now, then I need to draw 0.75. So therefore, I need to draw 75. Okay, here. So this 7.5 cm, which refer to 0.75 Newton. Okay, now this is the other factor. Now, then the resultant will be here. So I use my ruler. Like this, and then I draw it out. So you're using a ruler, you have 14.1 cm. Well, using a scale, you just divide by 10, so I have 1.41 Newton. Then this is the resultant. Now, you know why I asked you to use rulers. First of all, you need to use the ruler to draw the two red vectors. And finally, you need to use the ruler to find out the length of the resultant vector. Okay? So, well, there is still a question about like direction, right? Direction relative to vertical. This one I need to know how can I, because I'm not very familiar with this. So, I need to turn it. Okay. So, this is all I have here, right? So, let's say 32 degree. So therefore, it tells us that I have 32 degree here. Okay. Now I finish using the ruler. Maybe I just screenshot this and then copy, or for save, I save it first. Here, look at this. Save to photo. Okay, good. Something like this. So therefore, the magnitude of the resultant force is 14.1 cm. And the direction of the resultant relative to vertical, so vertical means this. So you need to give me this angle here. So how to find this angle? Well, you have, this is vertical, this is horizontal. Therefore, you got a right angle here. So therefore, right angle is 90 minus 32. So you got 58 degree here. So therefore, you put 58 degree here. Okay. So therefore, this is how we do it. Now there's, of course, we allow some range. I'm not saying that, we have to exactly 14.1, 14.2, not cm, sorry. It's 1.41. you may say like 1.40, 1.42, there's always a range. So that part is acceptable, but the direction, the method has to be correct. Okay, and then what can we do to change the size? Besides, the force can change the size and the shape of the object. Well, what are the two other changes we can do? We can change, well, there are many. Either two of them. So velocity, speed, direction, acceleration, deceleration, they all allowed. Some of you write FUMA here. Then I think you need to improve on your skills of reading a question. They're asking you changes that the force can or may produce. Instead of asking you for the equation for a force. Okay, next question. A long tube contains oil. A small ball is held at rest at the surface of the oil, so initially here. At t equals 0, the ball is released and begins to fall vertically through the oil. So this is something like the skydiving, because like you ask a skydiver to jump off the plane, it was at rest initially, and it fall down. When it fall down, there will be two forces. One is the weight, one is the air drag. Now in this case, it's not in the air, but because of the oil, there will be resistance as well. You can call it friction, that's also fine. So define acceleration. Well, this is the first test essentially. Rate of change of velocity. The mass of the ball is this one. Calculate the resultant force acting on the ball when it is accelerating downward at 2.8 meters per second squared. So we're given the mass, we ask the resultant force, we're given acceleration. So this one's simple. We can use F equal to ma. Because this F is really the resultant force. So therefore, 0.0075 times 2.8. Check unit, kg, good. Meter per second square, good. So we can just plug that in. 0.021 unit Newton. Okay, this is still very standard. And then now you will see the speed time graph that we see in the chapter of terminal velocity. And now describe what happens to the acceleration. What happens usually means, does it stay constant? Does it increase? Does it decrease? Things like that. How do we find the acceleration here? From the speed time graph, the gradient is acceleration. So here you will see at first I got a gradient like this, which is quite large, quite steep. By the end, it decreased to 0. So therefore, we need to say the acceleration decreases during this time, and at the end, it decreases to 0 at the end. Then we need to explain why it happens. Now, as soon as you identify that this is just a topic of terminal velocity, You remember that I spent the whole lesson to explain using forces how this can happen. So you can talk about many things. For example, why it decreases. For example, you may ask, what are the forces acting on there? So you may say the resistance due to the oil. This is really just go back to your learning journal. This increases as speed increases. So that eventually resistance due to oil equals to the weight. Therefore, no resultant force. So therefore, acceleration is 0. It's like that. So you look at this one, any fall up here. Now, some students, I don't know why they use the term deceleration. Then it will be not okay. Because first of all, just forget about physics, just using day and life understanding, there's no deceleration here, the speed is still increasing. Increasing in speed, increasing in speed, increasing in speed. At the end, no more increase in speed, but at least there's no decrease in speed. So it's not deceleration. You have to really think carefully. What is the difference between decreasing acceleration and deceleration? Decreasing acceleration means it's still accelerating, but just at the end, the amount of acceleration is smaller. So it's called decreasing acceleration. But for deceleration means you got the speed drops, decrease in speed. So this is a very different issue. On the graph, it's very obvious. Acceleration, the velocity time graph is still going up. Going up is still going up, but it goes higher and higher. So it's still acceleration. But this is different from a straight line. It means that the acceleration is not constant. If the acceleration is constant, well, it will just go like this. Then we will say acceleration is constant. Now the acceleration is curved like this. Then we set acceleration is decreasing. So that is the difference. So if this is confusing, then we boil down to the definition. Acceleration is the gradients of the graph. You look at the gradient. If the gradient decreases, then the acceleration decreases. If the gradient is constant, then the acceleration is constant. So the reason why we teach you the key message that acceleration is the gradient of speed time graph is just to save you from getting into troubles of misusing the term deceleration or finding it difficult to interpret this graph. Okay, now next one. By drawing tangent on figure 1.2, determine the value of the acceleration of the ball at t equals 0.01 second. So 0.01 second is here. Let me use another color. here, yes, 0.01. Draw tangent. That means I need to draw a line that touches it. This also not okay because I think it's like I move this line to here. Does it touch at the point I circle? It seems no. Let me change a little bit. I move this one to here. Oh, I think it's better now. This is like your ruler. I move this one to here and okay, so it touched there. So therefore, this is the tangent. Then I need to find the rise over run of this tangent. Then we need to read the graph carefully. It will start from here to here. Need to count bosses. Here, the run. No, this is the rise. And this is the run. The run is from 0 to here. Here is how much? Here I think it is 0.02. This is 2122. No. There's 6 of them. So this is 1, 2, 3, 4, 5, 6, 7, 8. So run is 0.028 second. And rise is like from here, which is 0.022 to 0.06. So 0.06 minus 0.22. So drawing the tangent, having the rise and run, we copy this down. So the rise is 0.06 minus 0.22. No, 0.022. And then run is 0.028. So rise over run. 0.06 minus 0.022. 0.038 over 0.028. So divide by 0.028. They get 1.357. Now your answer may not exactly than what we have because different people draw different tangent. But anyway, so 1.36 meter per second squared. Well, after doing it, why I spent so much time? Well, it's worth it. 3 marks. Usually, 2 marks are very simple question. 2 marks is we call one equation, write down the answer. 4 marks, well, you will need to write a lot. 3 marks, that means it's between 4 and 2. Okay. So there's a range is 1.2 to 1.8. As long as you're within this range, it's okay. Here. Distance between 2 stations. Okay, let's read the graph. Figure 1.1 shows the graph of speed v against time t for a train as it travels from one station to the next. Okay. So therefore, we can deduce that this is the station 1. One station, because it was a rest there. And this is another station, because the speed is 0 there. Correct? To arrive at the station, the train needs to stop. So find the distance. Distance will be just area under the graph. To find this area, we need to find the upper part, lower part, and then the height. I use a thicker number. Okay, what is this? The upper part is 130 minus 10. The lower part is 150. The height is, this is 10, this is 15, so here is 17.5. You see that? Oh no, I need to be careful. No, this is 18. Because you can count. I have 20 boxes for, no, there is 10 meter per second in 20 boxes. Now this is 10 meter per second because it's 10 here and 20 here. So the range here is 10 meter per second and there are 20 boxes. So in other words, I will have 0.5 meter per second in one box. You count from here to here. How many boxes are there? There will be 16 boxes. That means it's 8 meter per second here. So therefore here is 18 meter per second. Okay, then we find the area. 18 times this one, or this one is just 120. 120 plus 150 over 2. So let me see. Okay, 2430. Unit meter. 4 marks. It's really worth it. Yeah. I can use km. Yeah, it's also fine. Acceleration of the train in the first 10 seconds. So first 10 seconds, well, it's only here. How to find acceleration? Gradient. So the rise over run. Rise is 18. Run is 10. So therefore, 18 over 10, 1.8 meter per second squared. Now here you don't need to draw tangent because at t equals to, for the first 10 seconds, this is already a straight line. You draw a tangent, it will just align with the line on the graph. Okay, find the resultant force in the first 10 seconds. Well, resultant force, you're given a mass. The A is also fine, it's 1.8 meter per second squared. So therefore, you just F equals to ma. 1.1 times 10 to the power 5 times 1.8. So this is 1.98 times 10 to the power 5. Is it? Yes. My mental math is okay. Finally, they say the force generated by the engine of the train is called driving force. So therefore, the train, there's a forward force, we call it the driving force. And then now, during this interval of time, relate the driving force to any other force. Well, during this period of time, what happened? You find out that the speed is constant. The speed is constant. It means that there is no acceleration. So your understanding would be no resultant force first. We see on the situation, there is one force acting here. If this is really the only force acting on the train, That's impossible to have no resultant force. In order for us to have no resultant force, we need to have a force that is in the opposite direction of this force, such that they're of equal magnitude. Well, then the question is, what is this force are? Well, in reality, that will be the air resistance, that will be the friction, things like that. Therefore, let's call it friction. So therefore, when no resultant force, it means that the driving force minus the friction is equal to 0, because there's no resultant force, because it's constant speed. Therefore, the resultant force has to be 0. It's minus because they're in opposite direction. So therefore, the driving force is equals to friction. You can use the term air resistance, drag, that's also okay. Now, instead of saying that FUMA, now this one, if you write F equals to MA, there are two misconceptions you're having. If you write driving force equals to MA, the first misconception is this is not the driving force. This is resultant force. Resultant force may not be the same as driving force. How to find the resultant force? We need to think about what is the force exerted on the train. We have the driving force. We also have the frictional force as well. Secondly, the second misconception is, if you really want to say driving force equal to MA, A is 0 during that interval of time. Because on that graph, here, during that interval of time, there's no acceleration. So if you really put it as MA, you should put it 0. Driving force is 0. They found that something wrong. You found that you are not on the right track. Finally, there's also one more misconception, is that read the question carefully. They need you to write an equation relating the driving force to any other force acting on the train. So MA is not a force. We expect you put driving force equals to some force. So therefore, when you read the question carefully, you know that that can't be the answer. So I think partially that this part is also related to the terminal velocity, because it involves the concept of friction, air resistance, that when you have acceleration to 0, and then the object is still moving, and there's a force pulling on it, so there must be an air resistance to balance it out. Okay, so this is the case. So I'll upload this video to the class chat for a revision for tomorrow on the test. And right, if you still have questions, remember to ask me or ask your subject teacher. Don't get just stuck at one question and then don't know what to do. Ask your subject teacher or ask your classmate is also fine. Many of your classmates are very helpful, and I believe that through discussion with your classmates, you can learn much more. Okay, we stop here.